to write the compiler, basically generate the hardware instructions for the different generations of the hardware, and that was particularly in the network security domain. Then I have been working with Intel for last 1 decade, and this is particularly in the network space and the 5G space, and this is mostly in the radio access network. So basically, developing the hardware devices and the software stack, and basically doing the system architecture and developing the software stack for the 5G space. And currently, the focus area has been to infuse the artificial intelligence and machine learning onto the network workloads, including the 5G. So that has been one of the pathfinding projects that I have been working with along with the team at Intel. So this is more about here. Sure. So yeah, I cannot see the slides. So are you sharing the slides? Are the students seeing the slides?
No, sir. We're not able to see the slides yet. Yes, sir.
All right, so let's get started. So I'm going to present Intel oneAPI. This is a cross-architecture programming model. So as we take a deep dive, this terms will become clear. This is particularly, I'll give you the industry perspective, how things are evolving in the AI/ML space, particularly in the AI/ML space, but in general, high performance computing, scientific computing, or IoT, the media space, the graphics space, the natural language processing, and all of this, how things are evolving. So I'll give you the industry perspective and the challenges that we are facing. So yeah, so I gave you already an introduction. So this is all about. So agenda, I will start with oneAPI concept and then heterogeneous programming, and then we'll talk about the SQL open standard, and then the parallel programming. Then we'll discuss about what Intel has to offer in this space in the oneAPI tools and toolkits overview, followed by questions and answers. Yeah, next slide, please. Yeah. So let's discuss this one. So this slide is interesting. So if you look at the right hand side, this is if you look at the right hand side on the lower side, if you have XPUs. So XPU means these are all the hardware architectures and the hardware devices, including CPU, GPU, and FPGA. And these are expanding today like anything. So there are many companies, established companies as well as startups building their own AI/ML chipset. And on top of this, you have ASICs, and then you have digital signal processing (DSPs). So there are various kind of hardware devices, and on the top side you see the execution model. So some for following a scalar model, some vector matrix, especially the hardware device especially built for matrix operations. And then there is a spatial architecture. So if you see that you see the challenges here. So let's say talk about CPU and GPU. So this is like instruction set based architecture. So ISA based architecture. So if you, for the CPU, you have AMD and Intel selling x86 based CPU, but you have a ARM architecture based CPU. You have PowerPC based CPU as well. On the GPU, you have multiple vendors like NVIDIA, AMD, Intel, all have their own GPUs. And then FPGA is like field programmable gate array. So these are special devices. You have FPGA based NIC cards where you can offload compute intensive tasks onto the FPGA, and these altogether follow a different execution model. So now let's talk about the programming challenges for this. So if you look at the CPU and GPU, every vendor or every architecture follows their own set of sort of execution engines, and then They're on top of that, they have a firmware, software stack, compilers, device drivers, all sorts of toolkits coming together to make your workload run on the CPU and GPU. The FPGA, you can have FPGA coming from Intel or Xilinx. So this is kind of a spatial based architecture. So you write your logic and you expand your logic onto the space. So basically, it has millions of logic elements, and you combine all of these logic elements to form your logic. So basically, yeah, every logic elements kind of represents a truth table. So you combine all of your many truth tables to represent your logic. On the top hand side, you see the execution model. So a scalar means, let's say you have a large array and you want to do the summation of the all the array elements. So a scalar execution model, it will start with processing one data at a time. So let's say one array at a time. Then you have a vector wherein you can process multiple elements in the array element at a time. So, and this vector execution model is supported by the CPU and GPU, as well as all the FPGAs and ASICs. So basically, what you do is that you start processing multiple elements at a time. So for the CPU, you have a special instruction set like AVS instruction sets, or the SSC instruction sets, which lets you process 16 or 32 elements at a time. For the GPU, it goes even massively parallel, and it can process 32 or 64 elements at a time, and then it can divide its logic, all the data across multiple execution units, so that it can process thousands of elements at a time. So now you see the challenge here. So you have, let's say, talk about practical challenge that the industry is facing today. So let's say you have a IoT workload, or HPC workload, that running on a particular set of CPU plus GPU coming from one vendor, and then you want to port this particular model or particular workload onto some other CPU GPU coming from a different vendor. So then how much time does it take to port your code from one vendor to other vendor? So does it take days or weeks or months? So that's where the vendor lock-in comes in, and that's where oneAPI plays a significant role, following the open standard unified programming model for the CPU and GPU, as well as all kinds of devices. On top of that, there is one more challenge. Let's say you have a server where you have a CPU and GPU. Let's say on that particular server, you add one more data like FPGA onto the same server. And now you want to exploit FPGA as well for your workload. So basically, you want to distribute your workload, in terms of parallel processing onto the CPU and GPU and FPGA. So how would you do this? So if you have used vendor specific compilers, tool sets, and all that stuff, then it becomes increasingly very difficult to exploit FPGA for the same workload, unless you start writing remodifying your code and start rewriting the whole piece of code to run it on the FPGA as well. So these are the challenges. So basically, what I'm trying to say is that no common programming language, inconsistent tool support across the platforms. So these are the challenges today industry is facing. So let's go to next slide. No, so thinking about the parallel, right? So let's take on the left hand side, if you have a CPU architecture. So yes, you have an Intel Xeon server, and this has a there is an instruction level parallelism. This basically here onwards, try to think in terms of parallel. So in fact, massively parallel. So these are the today's need. Today's all the tasks or workloads are massively compute intensive, and you need to exploit parallelism to leverage the maximum thing offered by the hardware. So if you look at the CPU, what kind of parallelism is available today. So the one thing on the left hand side, you see the instruction level parallelism. So basically, you try to run multiple instructions at a time, and then SIMD level instructions, that stands for single instruction, multiple data. So basically, you execute one instruction, but you process multiple data. And then underlying it has a out of order execution model. So today's almost all the CPU architectures follow this. And then you are on if you slide rightwards, there's a hyper-threading model. So for every CPU core, you run two threads in parallel to keep the CPU pipelines busy. And then you have a 28 such cores coming together as a one chip. And then you have a 28 threads running. And then you combine these two chips together and which we call as a multiprocessing. So you have a multiple processors now. And then then you talk about, then we go ahead with the distributed computing. So think about it is as a cluster. You have a cluster which you have a lots of servers coming together to and offering you the compute capability. On the right hand side, if you see the GPU execution model, so this is a kind of very simplified model that I have drawn. So this is so on you see the execution resources. These are very small kind of processors, but there are thousands of such processors on the GPUs. And then you have a fixed function blocks. So every vendor is trying to differentiate themselves by providing a fixed function blocks. Let's say matrix multiplication is very important operation today, so they will write purpose built logic for doing the matrix multiplication. And for that matter, you have a in the AI ML space, you have a it's different kind of activation functions. So for different activation functions, you write purpose built logic as a fixed function block. And then you have a since GPUs are able to should be able to process huge amount of data at a time. So you have a caches and a high memory bandwidth. So specifically, you need a very high memory bandwidth so as data is always available for the execution engines. So these are the parallel primitives, all. And then there are companies coming up all together, different sets of hardware architectures to do the parallel processing. So now introduction to oneAPI. So oneAPI is the idea of oneAPI here is to provide you unified programming model. So you have a one single programming model which can run across all the GPU, CPU, FPGA, and all kinds of accelerators. So and then it also provides a heterogeneous programming. So now let's discuss what we mean by this. So oneAPI gives you a capability to write your unified C++ code, wherein you one single C++ code you write, and you can decide what basically a priori you decide what kind of parallelism is there in your code, and then you decide basically you take the whole workload and try to decide what code fragments can run in parallel and what are the sequential dependencies among the in the code. Based on that, you write a C++ unified code which will be applicable not only for the GPU, not only for the CPU. It will be applicable for the GPU and FPGA as well. So for example, for the GPU, you can there are other vendors which will ask you to write a CUDA code. And then there are other vendors which will ask you to write OpenCL code. So basically, every time you want to try some GPU, you'll be asked to write follow some programming model. What oneAPI does is that it gives you a unified programming model, basically one C++ code, and where you can explicitly express what is sequential and what is parallel, and then you decide where exactly your code would be running on which particular GPU or FPGA or CPU. So, and this is what we mean by the heterogeneous programming. So one unified C++ code, and then you can run it and across set of devices. Not just today, if you compile a C++ code, you specifically write for the CPU, and an entire portion of your code runs on the CPU. But in the heterogeneous programming using oneAPI, you can write one C++ code. Some portion of that code will be running in CPU, some other portion will be running on the GPU, and maybe some other portion running on the FPGA, and all in parallel. And the best part is that oneAPI follows the open standards. Open standards driven simplified language for expressing parallelism. And this is and then after doing all of this, what you want to see is that uncompromised native high level language performance. So every vendor will try to give you very optimized library which can run for very fast on their GPUs or CPUs. But the idea here is that all of the companies are coming together to have enhance this one API and then have their own tool sets, integrate their own tool sets onto the one API, so that you realize the native level performance, and it's up to them to figure out how they want to do it. But from developer perspective, you write a very unified, simplified C++ code. Then SYCL is an open standard programming model developed by Kronos Group. So what does SYCL does? So SYCL gives you uh, a capability to express the parallelism in your code. So and this is mostly coming from the OpenCL, but then it gives you at a higher level very user friendly abstraction. So we will see some piece of code. So basically, you try to figure out which part of your code can run in parallel. You specify that using SYCL standard, and then you create a kernel out of it, which we'll discuss shortly, and then you schedule those kernels onto a particular hardware devices. So if you look at the diagram on the right hand side, this is a SYCL standard. This is just a standard, not an implementation. So it gives you how to express the parallelism, the syntax. Then there are implementations for this. Intel oneAPI gives you a DP++ implementation. There are others which gives you compute CPP implementation and other implementations. From the DP++, if you look at the left hand side and go down, so the same DP++ code can run on NVIDIA GPU. So basically, what the NVIDIA could do is that translate this DP++ code onto a lower level abstraction, get CUDA abstraction, and it's their tool sets which will be responsible for doing this. Similarly, on the AMD GPU, they follow the ROCm programming model. So it's up to them to translate the DP++ code onto their programming model. Intel follows the level 0 APIs. So basically, you write one DP++ code, and that runs on across the different sets of CPU, GPUs, and FPGAs. Yes. So let's go to next slide. Yeah. No. So as we said, the kernel. So kernel is kind of this is not a new concept. Kernel has been used for decades in the OpenCL and CUDA. So we are so open in oneAPI also follows the same concept. It also uses the name kernel, but in the kernel you kind of write your logic which can run which you target for a particular device. And this is kind of so not you specifically target for a particular device, especially you just express your parallelism in terms of kernel. So you specify that this particular code can run in parallel, and I can schedule this kernel onto the some device, whether it's a CPU, GPU, or FPGAs. So kernel is kind of very simplified code, but massively parallel code. So you cannot have some kind dynamic polymorphism, dynamic memory allocations, static variables, and all those function pointers, all those funky things. You cannot write all of those in kernel. So those are only for the CPUs. The kernel is a very simple logic, but then you express your parallelism. So basically, it will be able to process huge amount of data in parallel onto a particular device. Then there are some expressions allowed, like lambdas, operator overloading, templates, classes. So these are the operations which are allowed. So on a higher level, what you do is that when you write your CDP C++ code or for your workload, you try to identify what part of code is can run in parallel and what kind of part of code has a sequential dependency. You break down all your code into a uh, large amount of kernels. So in each kernel you specify what proportion of your code can run in parallel, and all of those kernels get together. You build kind of graph. In the graph you have each node represents kernel, and each edge represents the sequential dependency. And then you write ask one API to schedule all of those all of these kernels, and in the engines onto a particular device, you know, honoring the sequential dependency among all of these kernels. Mhm. I DPC++ is, as far as I remember, it's for the x86, but I think I need to look at this. So basically, whether ARM has went ahead and adopted the DPC++, and they are providing the backend for the DPC++. So DPC++ is kind of higher level abstraction, but every vendor has to come and provide the backend support. So I'm not sure whether ARM has supported the backend for the DPC++, or they have their own implementation of SYCL. So probably you understand, like they can have their own implementation of the SYCL. So I need to see. I don't have this information readily available, but I need to see this. So I can get back to you on this. Yeah. Hmm. Correct. 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 Yeah.
Got it, sir. Thank you.
Yeah. So let's go to next slide. Or DPC plus is correct. So this is a language to deliver uncompromised parallel programming productivity. So this is again based on C++, and several constructs are coming from SYCL, and at the same time there is a push going on with basically the C++ standard and the SYCL guys are working together and to push some of the SYCL parallel expressions onto the standard C++ ISO standard. So basically the idea is to merge the SYCL and DP++ together at some point, to have your unified DP++ as a programming language. But the only as of today, if you see that what the DP C++ does is simple C++, which implements or extends C++ with the SYCL expressions for expressing the parallelism. Hmm. This is mostly C++ only. So I don't think there are other in addition to DP C++, there are other C++ implementations, but I think mostly it's a C++ based. So let's look at this code. This is a very simple heterogeneous compute code. So you try to include your SYCL headers, and then you have basically you use the namespace SYCL, and then you have a input string. So input string is something basically you want to decrement every input character in this string. So that is the whole idea of this simple DPC++ code. Now how are we going to do this? So let's look at line number 11. If you see, there is the input queue. So this queue is attached to some device. Now how to attach this particular queue to some device, that we will look at in the next slide. But for now, assume that this is a queue on which we can append some task. So on line number 13, we have a malloc underscore shared. So this malloc underscore shared is coming from DPC++. What this guy is saying that I want to allocate a memory which is accessible to the device as well as on the host. So host is kind of acting as an orchestrator, and you allocate this memory, and this memory would be available on the host as well as on the device. So what you do is that you copy the next operation is that you copy this data onto the malloc, basically shared memory, so that this particular memory is available to the device. And then from line number 16 to 18, this is what the kernel is. So if you look at here, you could have, instead of what, so basically line number 17, if you see, it's just iterating through all the input characters, and it's trying to decrement every character. Now, if you write the same logic for the CPU, you can simply run the for loop, and it will decrement every characters. But instead of writing as a simple for loop, what we have written is the q dot parallel for, and then how many elements you need to do this parallel operation. That is the size of the character string. So now you see that, now explicitly we are saying that, it doesn't matter whether you decrement the first character first or the last character first. Doesn't matter. You can go ahead and do this operation in parallel for all the characters. And then you finally you wait for the result, line number 18, and once the result is available, you do the print. No, so this is a one simple, very simple code, but explicitly we are saying that, you don't have to do this in sequential manner, every one character at a time. You go ahead and do this in parallel. Now, for the same piece of code, it would be compiled very differently for the GPU versus CPU and versus the FPGAs. And if you look at the line number 18, we are waiting for the result, but this may not necessarily be the case, and this is not generally the case. The reason is that when we ask some device or hardware accelerator to do some operation, we need not necessarily wait for the result, and because you have bunch of devices, like host is also an orchestrator, but at the same time it's offering you the compute capability. So you want to keep your CPU also busy doing all of the or rest of the task, while the some accelerator is or device is trying to compute the kernel. So it's our responsibility as a developer responsibility to figure out what level of sequential or parallel dependencies are there, and what piece of code can run in parallel while the device is trying to execute this kernel. Is blocked, is blocking call, correct. Correct. Any of the coprocessor, exactly. You need to free it also yourselves. So this is one level of implementation. So now oneAPI give you even higher level abstraction. So I'll give you one example. So here what we are doing is explicitly we are trying to copy the data so that the data is available to the device. But this may not necessarily be the case. So what we can simply try to without copying the data, we can simply access the data at line number 17. It's oneAPI, and oneAPI compiler and the runtime is intelligent enough to figure out that there is a data which requires copy from the host or orchestrator to the coprocessor. So all of this can happen internally by the runtime and the device drivers. So you did not do explicitly, but that requires different kind of semantics, like accessor kind of mechanism to share, to explicitly say that I don't care when the data is getting copied. You figure it out. You schedule the data movement, and you just give me the result. This is what my interest is. Yes, Professor Mol. Yeah. Yes. The next slide will become clear. So if you go to next slide. Yeah. Now that queue, right? So now if you look at the um, just after the try block, if you look at the auto queue is equal to GPU is available, and then you are trying to instantiate a queue using a GPU selector or the host selector. So this queue is kind of giving you a high level abstraction for the coprocessor or the device. So what you do is that oneAPI gives you a capability. Let's say you have a server, right? On the server you have a GPU and FPGAs and all kinds of other kinds of accelerators available. What you can do at the runtime, you can try to search whether this GPU is available or not. This is what we are trying in the try block. In the try block, we are saying that device test for GPU and GPU selector. So this will go ahead and look at the all devices attached over the PCI addresses and figure out the device capabilities and figure out whether there are GPUs available or not. If there are GPUs available, that it gives you a device abstraction, and based on that device, you can instantiate a queue. That particular queue would be attached to a that particular device. So queue is kind of giving you a higher level abstraction wherein you can uh, schedule your task on that particular queue. And this is what we mean by the heterogeneous programming. So basically, once the last kernel that we code, which is kind of iterating through all the characters and trying to decrement the characters, that particular code can run at the runtime. We can decide whether we want to run that particular code on the host or on the GPU or on the FPGA. Correct. Kind of shared memory, but it's an internal implementation. There is a lot of complexity involved. So everybody vendor tries to optimize, and oneAPI also gives a lot of optimizations. But from the developer perspective, you kind of give a higher level abstraction that on this particular GPU, I want to run this particular kernel. Hmm. Device s- device is same as the co-processor, as Professor Molly said, or or other all the other devices that we discussed so far. So basically, it could be host processor, basically CPU. It could be GPU, FPGA, or any device, or it could be TPU, tensor processing unit. It could be digital signal processing unit. So every vendor has to come in and plug in their device, plug in their hardware. So device means hardware. So plug in their hardware onto the one API framework. It could be host also. Yes. Let's say take an example. Let's say you wrote all of your workload, right? You figured out all the kernels, all the sequential and parallel dependencies and everything. But you have a single server. You don't have any device attached to any accelerator kind of device attached to it. Then you may want to run all of your kernels on the CPU itself. Exactly. Yeah. Yes. Now, this is another example. I have specifically taken the matrix multiplication because this is a very very common operation in the AI/ML space. So if you look at here, on the left hand side, if you have a work item, so basically each cell on the left hand side is defined as a work item, and there you have many such work items. And it doesn't matter whether which row or which column or which particular work item you are going to process first. Ultimately, what you want is the matrix multiplication, which you have been given two matrices, and you want to multiply and get the final result. So how to do this in parallel? And today in the artificial intelligence machine learning space, you have massively large size of matrices, and and you need to do the multiplication operation. So as I said earlier, every GPU tries to differentiate themselves by providing a special purpose built logic to do the matrix multiplication. But from oneAPI C++ perspective, if you see that, if you look at the code, you just explicitly say that, there is a range, one n and n, basically the rows and the columns. And then it's a range of 2 dimension, and then you go ahead and do this particular operation for every work item or for every cell. And this is how you express your code. So if you see that, this is a little different, but different from how generally we write for the CPU. But then once you express this level of parallelism, and then your job is done. It's up now. It's up to the one API and the individual vendors to compile this code, schedule this code on the particular device or hardware on the CPU and run this massively in parallel. Yeah, so host, correct. Host is generally a CPU, but it's kind of, you can say that it's an orchestrator which is try to orchestrate all the devices or the hardwares. So generally, when you write a C++ code, the entry point is been executed by the CPU. So you start with the int main, and then after that you start scheduling all of your kernels onto different set of devices. Hmm. Correct. Correct. Exactly. Now, this one API based toolkit. So basically, now let's come to the next level. So what we have discussed so far in falls into the direct programming. So basically, you write you start from scratch and you write your one API DPC++ code. You take the DPC++ compiler, compile your code for a for a for a for different set of devices. And then you have a DPC++ compatibility tool. So that is something is helps you translate the existing CUDA code or OpenCL code onto the DPC++ code. Then you have a Intel distribution for Python. So basically, these are Python extensions. So you may write your code in Python, and you may want to generate a DPC++ code and all those sorts of basically trying to make the developers' life easy. I think the particular interesting is on the right hand side. If you look at the middle one, the API based programming. So in the API based programming, let's say you have Intel math kernel library, data analytics library. So what does basically, so when you write your DPC++ code, uh, there are many. So basically, if you look at the mathematics, right? So there are different sets of mathematical operations, and it's maybe difficult for developers to write a very optimized DPC++ code for a particular architecture. So what this toolkit does that it gives you a set of libraries, so basically for well-known mathematical functions. So instead of writing your own logic for doing the mathematical calculations, you can simply use the Intel optimized math kernel library, which will translate your logic onto the very optimized representation for the hardware, Intel hardware. Similarly, you have Intel One API data analytics library, the Intel One API threading building block. This is another one very interesting. So basically, you may write a single threaded application, right? So you write DPC plus code single threaded application. So but then internally, Intel One API threading block will figure out if the parallelism in your code and try to run your code, basically spawn multiple threads and run your code in parallel. Then the one that requires mentioning is that Intel One API deep neural network library. So this is one DNN library. So if you have a deep neural network, so if you want to build a deep neural network, you don't have to build everything from scratch. You can simply use one API, deep neural network library. From those APIs, you can directly call some activation functions or some other mathematical operations or deep neural operations that you do. You can simply call the APIs and build your own pipeline. Then the one interesting is Intel One API collective communications library. So basically, now let's talk about the distributed computing. So in the cluster, you have one CPU. Basically, you have in the cluster you can have many nodes, and each node can have a CPU as well as as hardware accelerators attached to it. So now you think about HPC workload, some kind of massive amount of workload. So how do you process those workload? So certainly those workload cannot run on one single node. So you need to run those on multiple distributed nodes, which we call as a cluster. So cluster containing lots of servers and hardware accelerators. So Intel Open Communication Library gives you capability to internally schedule you all of these kernels, not only to the directly attached devices, but onto the others nodes or devices which are not directly which are connected over the network. And then on the right hand side you have a analysis tools. So basically, once you have written your tool, written your DP C++ code, you may want to optimize your code, figure out what is how your code is doing. So this is where Intel VTune Intel Advisor comes into the picture, which helps you write a very optimal code and gives you an advice like where exactly the optimizations opportunities are. Mhm. Mhm. x86 architecture, yes. Mm. Yes. Correct, correct. You say Intel decision to provide all of these libraries to to ease the developers life when they are trying to run the workload on the x86 architecture. Next slide. Yeah. Now, so now we have a on top of base toolkit, you have a core set of high performance tools for building DP C++ applications and one API library based applications. So you see that Intel one API, HPC toolkit, IoT toolkit, these are all available on the net. You can go ahead and download and try it out. One API DL framework and for the rendering, AI analytics, this OpenVINO system bring up toolkit. So all of these toolkits are available, and you can download and go ahead and start doing the basically all of these has ready built-in examples also to get you started really quickly. Yes, Intel Dev Cloud is there. Yeah, yeah. In my opinion, I think it should be available. So I need to confirm this, but for the students, I think it should be available. Correct, correct. Yes, yes. Yeah, please. No, so this is Intel VTune Profiler. So it's a very strong tool offered by the Intel. So it analyzes the DP C++ code. So VTune is not a new thing for Intel. This has been there for decades, and we have been using this for the optimizing the C++ code, C++ code onto the Intel hardware. But then now this has been extended for the DPC++ heterogeneous programming. So this understands, you are running DPC++ code which is trying to execute your kernels, onto the hardware accelerators as well as on the host device. So it's highly tuned for CPU, GPU, and FPGAs. And if you look at the right hand side, it's for the GPU. Let's say on the lower hand side, on the left hand blue box that you see, it tells you like the you know GPU was active 10% of the time. It was stalled 50%, 52% of the time. The GPU was sitting idle for 36% of the time, and then there were 20 threads active, and the occupancy was low. So basically, it gives you overall picture like how well you are utilizing the GPU. If you look at the bottom, look just below the bottom of this, on the right hand side picture, it gives you the CPU utilization also, which is a 24%. So this is kind of giving you a high level overview like how well you're exercising the parallelism in your code. So, and how well you're exercising, probably there are chances that there are other bottleneck in your system. Probably the memory is the bottleneck, IO is the network IO is the bottleneck. So you need to, it gives you a, like, hint, like, where exactly you should start focusing on to harness even better the hardware capabilities. Yes, yes, correct, exactly, exactly. Function level. Yeah, it can go to function level, and it can give you exactly the line of code where exactly your code is installed, probably waiting for the memory or something. So, and how many cycles it was waiting for that particular data. So it will give you a very fine granular, report, where exactly where, and also it also is, sorts the result so that you can start focusing from the top one, which is the highest, kind of, instruction which is kind of stalled, not able to execute. From there, you can start addressing all the code, all the, bottlenecks in your system. Exactly. Yes. 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 This is Intel Advisor. So let's say you have your workload or DPC++ code, and which you have written for the host, and your kernels are also running on the CPU itself. So if you look at the right hand side, original, this is host and CPU. Basically, all your kernels are running in the CPU itself. Then you gives you, like, how much time did it take for the overall operation to complete. Then it gives you a kind of advice, like if you use a particular accelerator, then what would be the cost, how much acceleration you will get if you offload these particular kernels onto some GPU or FPGA or some, or some device. And at the same time, it also takes into account the data transfer cost. So the moment we start using any other devices, you have to take care of that. You take time to transfer your data from the host onto the device, right? So it takes care of the data transfer cost also. And effectively, it will tell you, like, how much time you can save if you start up or start using, hardware accelerators. So, and this will also, give you, like, if you look at the left hand side, vectorization advisor, it will tell you that which particular piece of code can be vectorized. It gives you a threading advisor also, like, add effective threading to unthreaded applications. So, it will tell you, you can add these many threads to run this particular piece of code, so as to run your workload even more effectively. So this Intel advisor is really very powerful to guide you for the application optimization. I felt guys, and there are other tools. It's not, I think, if I remember, this is not part of one API, but there are other tools, provided by Intel, which will give you estimation of, how much of power is consumed by your particular workload. So this is the last slide. So this is toolkit's free availability. So you can go to software.intel.com oneAPI. So you can download from there. If you are using the Linux machine, you can directly, do yum install, apt install, depending on the Linux distribution. At the same time, you can register yourself with the Intel Dev Cloud and try the one API there. So the easiest, I mean, you can go to Dev Cloud and you can, try different hardware devices. And to quickly get started, you can just take a server, any Linux server, download the one API and try out the, basic examples and get started with it. Yeah. Hmm. Yeah. So for the industry, I would say that there is always, at least it was true for me. So there is some kind of little bit of disconnect between what has been uh, what has been taught and what has been shown as a very compelling problem statement in the academia versus in the industry. So you will see that there is some kind of disconnect there. But at the same time, if you start focusing on the real world problems, you may not be able to solve those real world problems yourself at this point, at this stage of your career, because this is too early for you to solve real world problems. But if you start at least imagining that what the real world problems are, and start thinking in that direction, so that will give you a very strong edge compared to other students, so basically other people. So at least the realization of this is itself is a big achievement. So you try to crack the right set of problems which is going to be effective for the industry and for the people across the world. And regarding skill sets, everybody has their own individual perspective, right? So, somebody may be interested in more towards the networking side, computer networks. Somebody may be interested more towards the hardware architecture side. Somebody would be interested in building the kernel or operating system. So every a space that you take a dive in, there are opportunities out there. So you need to basically decide yourself what particular area is of interest for you, because that is the key to for you to survive for a long term, build a long term career in the industry. So if you know that this particular subject or this particular domain is of interest for you, then you go ahead and take a deep dive into that, on that particular subject. You go ahead and probably take extra courses, most importantly, not just theoretical courses. You try to do the hands on as well, and try to figure out. So at this stage, again, I'm saying that you may not be able to reach to an industry standard where the today industry is, but at least your interest itself would be a very compelling reason for industry experts to hire you. Yes, yes. Professor Mauly is an example, right? So continuously learning, so throughout the life, yeah. Yeah, so this is kind of, very, everybody has a different perspective on this. So on using the ChatGPT. Yeah, so in my opinion, for me, I also, get into the ChatGPT and ask questions, but then ChatGPT is kind of a starting point for me. So if you want to get started with some terminologies, or with some ideas, so ChatGPT, you can ask ChatGPT, and this ChatGPT is good at giving you the state of the art. So let's say you want to solve some problem. ChatGPT, ask ChatGPT, it will give you the exact piece of code or exact set of ideas. But then what ChatGPT is giving you kind of already learned data. So that data has already there in the web. So it has learned from there and it's trying to imagine from there. It's either trying to give you the same data, or it's trying to take that as a starting point and give you some imaginary data. So for me, ChatGPT acts kind of in a starting point. Basically, that's where the current industry is, and from there you start your stuff. So don't get too much obsessed about the ChatGPT, and what ChatGPT says is really like very truth, kind of the truth and divine statement. So it has its own set of limitations. So you may take ChatGPT as a starting point, and you may want to go ahead with that. But importantly, I think probably since you are talking about the ChatGPT, so you may want to learn how ChatGPT is able to answer those questions. So this is something very proprietary information which been processed by couple of OpenAI or some couple of companies who knows how exactly the things work. But then this is certainly interesting, and you can start developing a sense like how the what the prompt engineering is, how the data is getting generated. You try to understand the background of it. How ChatGPT has been built, and it's not only the transformer kind of model. It's entirely altogether a complete operating system. Different sets of tools coming together to make the ChatGPT work. So you may want to explore at least some areas of ChatGPT, how things are working. Yeah, so yeah, correct. So Intel Advisor, kinds of helps you. You may not think about the situation. You have a host or the CPU, right? Or you may not have access to the GPU. Or you may not have you are just thinking about how much is it worth investing your money on the GPU or the FPG or any other kind of accelerators. So either you company gives you a dev cloud kind of environment where the hardwares are already installed and you are trying to run your workload there, or the other possibility is that you take the Intel Advisor and you try to figure out if we start using the GPU or the FPG or for that matter TPU or any other accelerators, then what would be the advantage that you will get, and you may not have access to all other accelerators, right? So this is where the Intel Advisor comes into the picture. Even if you talk about the GPU, there are several generations of GPU. This is not just one generation of GPU. So and you may not want to over invest on the GPU, right? So basically, you may want to choose the GPU based on your compute or workload requirements. So Intel Advisor kinds of play a significant role in deciding in letting you decide how you should be running your workload and what hardware devices you should be choosing. Hadoop is altogether, it's a big data framework. So I am also not, I have also not used the Hadoop and all these systems, but then those are altogether, uh, altogether built to address different kind of, workload requirements. So there, I think probably the database systems are more important. So how you define the database, distributed storage, and all those stuff. Yes. So very good question. So what is happening is that if you can, so basically, you can on the internet. So I'll show you. There is a Unified Acceleration Foundation, UXL Foundation. So UXL Foundation is going on top of oneAPI. And if you look at the UXL Foundation members, so these are companies like Oh, by the way, ARM is there. So ARM, Intel, Qualcomm, Samsung, Google, Broadcom. So all of these companies have come together and enhance the one API even further and plug in their hardware devices as well as incorporate the SQL standard as SQL is going forward. So they are contributing towards, many of them are contributing towards SQL also, enhancing the SQL as well as their C++ implementation to incorporate those SQL enhancements. So this is so earlier, Intel was kind of taking the lead in all of these efforts, but now there are several companies who have come together to build the follow the same follow the same philosophy of multi-architecture and multi-vendor software ecosystem and unify the heterogeneous compute ecosystem. So I'm just reading from the Unified Solution Foundation. So you can just uxlfoundation.org. So this consortium has been built recently, and actively people are working to build this whole ecosystem. UXL, yeah, yeah, uxlfoundation.org. No, not really. So thank you, Professor Molly, and all the students for attending this session. Yeah, yeah. So thank you. Bye.
Thank you, sir. Thank you, sir. Thank you, sir.